Okay, good morning, students. So, do you have doubts, queries over last week or past several classes? Do you like to ask any question? Okay, no question. No question about the last week test. This Sai Vardhan is there.
Yes, sir.
No question about last week class test.
No, sir.
Okay. Okay, I just want to get an impression. Is this do you have any critical comments over the class, or you are all okay with the class?
Like it would be helpful if there's a MATLAB tutorial class because many of us don't aren't acquainted with MATLAB code.
Mhm. Actually, good. At least you have pointed out some issues. Basically, this course prepares you to the theoretical side, or the more of prepare everything except the execution part, right? So prepares everything means starting from a problem statement, you have to write the balance equations and frame it in the form of differential equations or algebraic equations, prepare everything, the models. But model evaluation in terms of solving simultaneous algebraic equations or differential equations is just basically the laboratory component. Okay, so fourth year, first semester, you have a lab called Cape Lab. So if you go to that lab, I mean, next year, this year, summer, July, August semester, you will find that Cape Lab is nothing but about 6 to 7 problems that will be given to you for solving. Now, those problems invariably will require the use of this concept that we are discussing in the class. There it will be asked you to solve. Also in that Cape Lab, I don't know whether any tutorial kind of the Matlab training or Matlab handling how to use Matlab will be provided or not. So I'm not sure about that because I also do not teach Cape Lab. But so I tried to devise or to prepare this course material at least to some extent that you solve the problem based on the codes available. So I believe I have given you the MATLAB code, and many of you have MATLAB with you. Also, the online version of MATLAB is accessible. You can access that too in our Cape Lab in our department. So using MATLAB is not difficult for you. The thing is that you have to practice the codes that I have sent for different problems involving algebraic, ordinary differential equation, and let's say if we come across across of unsteady state partial differential equation. Hmm. So that is my statement regarding the MATLAB tutorial or training. Um, Only thing I can ask you that you practice the code, run it on your own computer, change the limits, change the constants, parameters to see just what happens on the results on the output side. Hmm. This
And like
much I can. Bolo.
maybe some YouTube links that are already available, if you could share them, that are required for the course, please.
Okay, that I can try, but I more or less will prefer. There are actually MATLAB videos in directly mathworks.com website. There are many tutorials. Of course, those are very precise and short duration video. You might not fully understand those 2-3 minutes short video, but they are actually very specific to the particular problem. So knowing that, you can now broaden your idea and by just internet from YouTube videos or something. I will try to post or some link for the execution of the problem, but I believe that the problem class in the discussed in the class involving the codes or use of code, you practice it. Huh? More and more you practice, you will understand, because few of the genuine I mean not I mean like yeah, the major concept that were discussed are basically linearization, then steady state analysis of the stable points, stability analysis of the steady state points, and then transient operation where the stiff equations are involved. So these few things invariably you will find in your CAPE lab course in next semester, that some of the problems given for exercise in the laboratory course will be coming from this. Hmm. So it is very essential that you go through this course material, practice the codes more and more, because if you come across difficulty or if you come across any problem with the running of the code or framing the equations, model equations, then I am always there. So, but that initiative I'm expecting will come from you. That we have, sir, we have tried this code, but it is not working, or something like that. So that much I can say. Hmm. Cyber then. Mm,
Yes, sir.
I okay. Any other want to make some critical comments? See, this I actually wanted to give as assignment, which I'm getting delayed. So the deadline, of course, I know that there are many other assignments, and in the coming few weeks you will have an mid-semester examinations from 21st. But you have 20 days in your hand, so practice this problem. Consider it to be an assignment. Deadline will be not very near, it will be at least 10 to 15 days will be given, but I really want that you practice this, because this has been a similar problem has been shown in the class. We have spent a lot of time on this. Maybe we can again, if you come across any problem. So both graphical method as well as the mathematical method, so linearization technique and graphical analysis we have done. So all you have to do is to solve the two equations to get the temperature and concentration profile, okay, over the reactor, and then you then you apply the technique to analyze the steady state points. First of all, you have to see how many steady state points you are able to see. So this is your second assignment. I will post it in the Cape this general channel, and practice it along with the MATLAB code, so that you will understand and you will get your concept very clear. Okay, so I think I have summarized the major points that till date we have discussed, and mostly by today's class, it would be more or less some to some extent it will be covered, that what is basically models that we have derived from our governing equations, governing principles, the typically different transport and reactions problems, So that will be the summary, or that will be the areas that is there in the syllabus. From tomorrow's class, it will be tomorrow, and maybe next week Monday, some part of the class will be focusing on the just basics of ANN technique, artificial neural network, just the commonly used technique called feed forward neural network backpropagation algorithm. So that part I would discuss in the next few one class, or maybe half of the class of the next week. And after that, as I said in the very beginning, that there will be term projects which where you individually have to solve your problem. So or maybe I can give a group also, because there are large number of students, so maybe 2 person a group. So you have to submit a report kind of thing, not in a detailed manner, but at least starting from scratch, the problem and definitions will be given. But after that, the probably kind of a schematic, and then IFD, and then model equations, then solving, then MATLAB code results, everything. So you will be given time. So what you can understand, that these assignments, class test, or term projects are constituting major elements in your evaluation. So mid semester and end semester will be always there, but this time I would certainly will not focus much on the mid semester question, or not question, mid semester marks. I think I have already given you an idea about the divisions of marks in different uh, portions: assignment 1, 2, and dot project. They constitute large marks. So just practice and practice of the codes, the problems that have been given, the assignment 2, which will be posted today, and then you will focus on the term project, which where individual a group wise problem will be given, and you will be asked to prepare everything as I discussed. So those problems will be first discussed in the class. Then the problem statement will be given. So those are basically applications we will see later on. So now today it will be mainly the some extension of the technique that we are using for solving ordinary differential equations. So till date we have seen the ordinary differential equation of first order, of initial value in nature. So we have dealt with simultaneous equations, coupled equations, temperature, concentration, um, for example, transient CSTR, and we have solved them initial value problem under the category of initial value problem. So we have seen where a steep problem or a non-steep problem, there are different kind of solvers we have seen. So today we will be mainly looking at other kind of problem which are called boundary value problems, and mainly these boundary value problems, what are their nature, and how do we approach for their solution, and what are the typical applications of this kind of boundary value problems in chemical engineering uh, subject. So let's say, though I have written a thing that what does this solver do in MATLAB. So basically this is an kind of like ODE 45 in or IVP, the initial value problem, or ODE 15S. Similarly, this BVP4C, this algorithm is this solver is basically based on the collocation method. Okay, so one of the technique, whether you have studied it in numerical methods or not, I'm not sure, but this is a one of the technique for solving uh, boundary value problem. There are other technique called finite difference method. So these two are basically workhorse of solving boundary value problem. Okay, so a little bit discuss about this BVP4C, and then we will go to the solution part. So first let us see that what are the different type of situations that we arrive in transport, generally transport problems. For example, momentum transport, or temperature or the mass. So there we generally have, let's say, if temperature then dt dx, so we get a flux. If velocity, then we get tau, the first derivative, mu du dy or dv dy, and then we have the other one which is called dna dz, or if it is a one-dimensional, so molar flux, moles and molar flux. So all you have to see here that let's say proportional to dv dy, and it is also proportional to dt dx. I have just taken one dimensional, okay, for the sake of easy understanding. I have just taken one dimension, k dt dx minus k dt dx. So you would identify that here the it is basically a variable is one, only the temperature. So one is the single this t, and another is the its first derivative. Okay, so generally when transport related problems we appear or we come across second order ODE. Okay, second order ODE. Most of the transport problem, they have the characteristic that we come across a second order ODE. This is their particular nature, transport problem. Now, a second order differential equation can be reduced to two first order differential equations that we know. Okay, but that does not make it an initial value problem. Okay, that does not make it initial value problem, because there are conditions over which the values are specified. In order to solve the integrations, you need some values at t equals to 0. Let's say it's an initial value problem, or at some locations you have to you have to have the variables that you are going to solve through integration. The values are must be specified at some point. So in case of boundary value problem, basically at two different locations or at two different points, the independent variable that you are not the independent variable, at two different points your either temperature or flux is given, or velocity and their shear stress is given, or the molar moles or the molar flux that is provided. So at two different point it is provided, not just at the initial point. So typically let's say these examples we can take and just reduce it to two boundary value problem, two ordinary differential equation. Let's say from a mathematical angle, just we see this, that double derivative. So it is basically the what is called y double dashed and mod of y equals to 0. Okay, so we can just very easily reduce it to into and to at 2 points the boundary conditions at y at location x equals to 0, the value is given, and at y x equals to 4, a value is given. So at 2 point the two boundary conditions are given. Now we can reduce these equations into two first order ordinary differential equations. So what we will do, let's say y1 dash first derivative of y1 equals to y2, and then y2 dash will be equals to minus of mod of y1. All right, so what we have done, so we have just made it into two ordinary differential equation, right? So here in this problem we can say that here our y1 equals to y and y2 equals to y dash. Okay, so just take this, substitute here, you will get this equation only. So generally we can consider that this has a nature or this can be the problem structure is like this, and at two different points at A and B of the independent variable, that means at x equals to A or x equals to B, the two values of y are provided. So this is one type of boundary conditions. There can be other type of boundary conditions which I am not going to discuss now, but uh, just they can be of different type. Maybe the flux is given at some other point, or some other or it's a mixed type of conditions, mixed boundary conditions. So those are of altogether different categories. So what we wanted to emphasize is the technique that we are going to use, and in general we come across in the transport problem, let's say steady state heat transfer across a slab, or diffusion across a slab, or diffusion reaction across a slab. So these are the examples that we will be mainly taking in this today's class, and approach is the same. We have to use this BVP4C that we will be discussing after some time, I mean in this class. But typically this is the approach, that you have to first identify the major equations that you are going to solve, and then you have to make sure that you know the boundary conditions, and you have to carefully evaluate that what type of boundary conditions are given. Generally the variables are specified, if not their first derivative are given at other points. So accordingly you have to use the MATLAB code. So like previous, we will be now discussing very thoroughly, one by one, the what we are going to do with this kind of equation. So let us take the problem first, and then we come to this particular execution part. So it is basically the steady state heat transfer across a slab. So let's say this is your case. So heat is just heat transfer across this x-axis, across this wall. Hmm. And other two dimension, let's say this and this, we don't vary the x. We don't vary the temperature. The temperature is not being varied on the other two dimensions. It is just the one dimensional problem, steady state heat transfer across the slab of thickness L. So let's say within this, uh, this is the L. So within this length, we are just interested to see the temperature distribution, temperature profile. So that is the typical equations that we have in the heat transfer problem, that flux equals to this rate of heat generations, and if it is an insulated wall, then we consider oftentimes this to be 0, and then this equation reduces to this. So it can be, there can be two cases. One is the thermal conductivity of that solid material, which depends on temperature. Sometimes we keep it as constant. So if it is a constant, we can take it out, or if it is a function of temperature, can be of this or t square or some other functions which will make it non-linear. Little bit complicated, but we can solve it. So what we have essentially the equation. So as you can see that this is a second order ODE, second order ODE, and we have this at two conditions at 2 point. So x equals to 1 we have written, but we have actually taken the non-dimensionalization form. So we are not writing x equals to L, but in this form we often do this in the transport problem, or diffusion reaction problem, or just diffusion problem. We often do this kind of technique, non-dimensionalization. So based on that, we change our boundary condition to this type, and we know that we have now two variables. y1 and y2 like previous in these examples that I was giving. So, so basically, what is the structure of solving this problem? Structure is like this. We have on one hand the major equations of containing the differential equation. So as previous, the right hand side of the differential equations, or not only the right hand side, the major elements of the differential equations. Okay, so other will be basically the functions, differential equations, the functions contained in the differential equations. The second MATLAB file will be containing just the boundary conditions. So this is something extra. Extra means like when we had solved IVP, initial value problem, we didn't have to specify a M file for just specifying the boundary conditions. What we had to do, we had to just give the function file of the differential equations, if that is coupled with algebraic equations. For that we had to write another M file. But for specifying the boundary or conditions, initial conditions, we didn't have to write any MATLAB file. But here we have to do it because of this condition that the solutions that will be approximating, because ultimately we will solve it through numerical methods, where we are almost like are unable to do it analytically, or even if the analytical solution exists, we are trying to compare it with our numerical technique where we have just digits or data at different points. Okay, so the very essence of numerical technique is that you don't get continuous lines or continuous thing, you just solve on different points, different mesh points or different in incremental points at different step size or something. So basically you have the solutions of this BVP4C kind of solver. That actually does is basically it approximates the solution over different points, and that approximation in the form of a polynomial has to satisfy the boundary conditions. That is the major criteria here, that it instead of what we had earlier have seen, that it follows that what is called RK method or something else, where we though those were uh, also will give data at different points, but they were based on certain algorithms. But here it is something different. So collocation method actually approximates the solutions over a range. That means if this is your x equals to 0 and this is your x equals to 1, then at the two boundary your temperature is given, right? Now what it does, it divides the space into equally sized points or region, and over this small region it approximates a y. Okay, so it approximates a y means it uh, y is a kind of certain degree polynomial, cubic spline or some functional form. So that has to satisfy this two boundaries, not only the two boundaries but also the solutions across each of these grid points. Okay, so it requires two initial guesses. So I'll come to that initial guess part little later. But what we essentially understood from here is that this kind of solution approximations must satisfy the boundary conditions. So we have to write the boundary condition separately, so that the functional approximation, it recognizes that boundary conditions are there and it has to satisfy that. So it has to solve, or it has to rather calculate based on that mesh points or the x equals to 0 or x equals to 1 in that functional form. So since it is calculating by taking that value of x at its boundary to just evaluate the functional value or y, that's why it is requiring another functions, another M file. So basically two M file, that one for differential equation, one for boundary conditions, and one is the major file where you will solve it by calling that solver, major main file, the main script file. Okay, so now coming to that initial guess part. So what actually, so this is basically MATLAB's syntax. You have to use it. You have to use. So this actually initialization is basically the solutions that is going to be initialized. That is going to be initialized, by like this. So what it does, that it can be 5 or 4, some number of equally spaced points, and in the range of the range that is given 0 to 1 in this particular problem, and it requires two values, two values as an initial guess. So what are these two values? Since it's a two second order differential equations, we must provide the values in order to solve it. Now this that is the major trick here, providing initial values so that it starts the approximations, and functional form gets validated or gets valid over over the individual range. And when you get ultimately the results, or when you get the temperature x or y versus x, it should match, whether linear or let's say a non-linear form. It should satisfy the all the boundary points, okay, all the boundary points as well as the intermediate points. Now, one essential understanding is that the providing the initial guess is very can influence your results a lot. So I will just show from mathematical aspect that one example problem where two different initial guesses can lead to different type of solutions. So we will show that part little later. So one was plot like this and another was like this, I think. So just initial guess, how to provide initial guess. So initial guess are nothing but, generally people take the in the range of 0 1 or 1 0. So typically they start it with it. But what I understood is that if you know the physical origin of the problem, right, if you know the physical origin, so for example, you know that temperature must lie, or temperature must get distributed from this point to this point. So for example, a steady state heat transfer condition conduction problem, you know that temperature profile will be kind of linear, or rather it will be linear. And linear, not only linear, but also it will lie between these 2 points, right? So at least initial guess that you are providing should contain one of the ends. So that is one trick. So if you know the physical origin, if you know the physical picture of your problem, that you are essentially kind of can speculate that, or you can guess that the temperature would fall or concentration would rise, or velocity will decrease in that profile. So in that sense, you try to give the initial guess by satisfying one of the boundary points. So that actually makes the initial guess structure file, and that is one major step or writing script in the main file. The second one would be the solution of the main differential equations, or rather the system of equations, ordinary differential equations. So we have written one M file for the differential equation, we have written another M file for the boundary conditions, and based on the initial guess, so these three are major input or feed in order to solve it, so that we get y and t and x, or y on x distribution, y and x. So I think I have also categorically I have written here that this is the first M file, where you have just written the right hand side of the equation. So we have broken the equations into two, as we know that one is the variable t and other is the flux. So flux is 0. So do you want this, just we have done some mathematical these formulations, and accordingly we have also made these boundary conditions at. So this is at x equals to 0, this is at x equals to 1. So y1 refers to the variable, first variable, that is the temperature. So the value is specified at the boundary. So if one t I think is specified at left, and on the other side it is the q, then I think it is Dirichlet or Neumann. So there are different kind of boundary conditions. One is mixed boundary condition, one Dirichlet Neumann. So just go through them, you will understand essentially that either flux is provided, or the variable but the essentially which you are going to solve is provided, or there could be mixed. So this is how we just write it, and the major heat transfer equations of the second order ODE. We break it into two, and then we write the two variables P and Q. The second is the boundary conditions. So this is a particular structure that we follow. What we essentially do it is that to be zero, to made it to zero, to made it to zero. That means it calculates based on the functional approximations, and it has to satisfy the boundary conditions y a and b. That means at x equals to a and x equals to b, that is the functional values of y and variable, and it has to satisfy. So in that functional form. So I think the boundary condition was right like this: y1 at right equals to 1. So what we made in it like this as a functional form. So right hand side is basically 0. So residual, it just creates that syntax in the Matlab. It makes that when you put the values in the functional form there and make it as a function equals to 0, in that way. And then comes the major part, which is your called major script file, where you first you actually give the initial guess values. Based on that, you call the solver to solve the values. Here the typically this actually divides the point into 100, the range 0 to 1 into 100 points. Okay, now in the previous step, that is in this step, it has actually solved the y as an x at different points. But now or rather not only at different points, but at different five different points in the functional form, that collocation methods BBP4C. So it has just got from just this particular range. In order to make the plot more realistic and more looks like a continuous one, I mean, we have divided the range again at 100 points, and we have just particularly then further calculated the y at other points. So the structure or the solution is reached here. It has solved it, but now it is further calculating at other intermediate points to make a good plot like this. This let us see in Matlab. We have done it in Matlab, and then it will be more clear to you. So let me share the screen. Okay, so I think you can see this. This is a, as I said, two function file, one for heat transfer equations, one for the boundary conditions, and one for the major main script file. So what we have done, we have just typed the code, and we are going to solve it. So few things to be remembered here. One is the giving the initial guess or initial structure. So this is again required in order to approximate that functional behavior or functions approximations of polynomial of certain degree in that different collocation points. And once that is satisfied, so depending on the initial guess, it can give you very different results. So I will show that. Just let me finish this solution part. So what we are going to see here is temperature and its flux. So essentially we can understand that we have started the equations by writing flux equals to 0. So we will get the constant flux, right? So we can expect that, and temperature would increase from left to right, or it will decrease in that yeah. So since it is k is a function of that temperature, so one can expect that plot is not exactly linear, right? So had it been k to be constant, I think it would be more linear, but here k is a function of temperature. We have given here that k equals to 1 plus alpha y1. Alpha was a constant, but this what is called y1, that means t. So we can expect the temperature to be little bit curved in nature, and flux to be constant. So this is our before we solve, if we can make this kind of good educated guess about the results, that gives us more insight into the problem. This is very important. um, Once you practice more problems, this skill will automatically be developed in you, that before actually going for solution, you are kind of, you can foresee that this temperature or the flux, or let's say temperature or concentration, or let's say velocity or velocity gradient, or the shear stress, so how they will behave, how they will change over that region of interest. So be it algebraic equations or ODE IVP or ODE BVP, so you can easily speculate that, you can easily find out that how the what would be the expected behavior. Hmm. So let us run this file and see what happens. First let me clear it. I think I have to share the whole screen so that you can look at the plot. Okay. Okay, now I'm starting it. So it has divided the range into 5 points, and also given the initial guess as 0 and 1, and then again this is giving us 100 points. D eval is just evaluating that y again in that solution that is obtained, and at different 100 points, intermediate points. The figure 1 will plot the temperature versus x, and figure 2 will plot the heat flux versus x. So now I think you can see here that so this is the temperature and this is the heat flux. Okay, so here we can see that as we specified that 2 boundary points, so it is achieved, and it can approximates the functional. So the collocation methods gives a good results, and it as expected, and changing the initial guess can influence, which I have not tried here, but you can just see whether you are getting some absurd result or not, because it has to satisfy the 2 boundary points. So one of the initial guess, giving good educated initial guess, is that you maintain one conditions at one boundary, and accordingly the intermediate points it will approximate. So this is the heat flux equations. Over the range we just get a constant heat flux, and this is the temperature range, temperature distribution. See the nonlinear part, little bit curve is there, so because of the k is a function of temperature. Okay, so let us now so this is this clear, these two plots, or any question? Is this clear to all of you? Achal Kumar, Anik Mandal.
Yes, sir. Ajal Kumar. Yeah, you.
Ach- Achal Kumar, you are there?
Yes, sir.
Hmm. So, did you understand this BVP4C?
Not exactly. I have to watch the lecture again. Like
No,
the
right now can bolo, bolo, bolo.
yeah, well, I'm not quite comfortable with MATLAB. I just sometimes use the Jupyter Lab. That works fine for me.
Okay, but essentially, you it is not that you have to know MATLAB, but it is something just the reverse way you can think of. But if you do not use MATLAB, there is a major element that you are missing in chemical engineering curriculum. So it is not difficult to learn MATLAB. That is the point.
Okay,
MATLAB
sir. I'll
has
try MATLAB.
Yes, MATLAB has actually it has actually the workhorse in engineering problem has been, and every year they actually update it by adding new features. Nowadays, people also do this neural network calculations, complex modeling problem in MATLAB. Hmm. So don't just skip this MATLAB part. I know you will be able to solve this problem by using other other language, other maybe C, C++, or Python you can use. But knowing MATLAB, it will help you to explore other side of chemical engineering problem. See this boundary value problem, you have to otherwise if you solve it in C or C++, you have to use you have to write your own subroutine. You have to make your own subroutine to integrate the equations. So, but if you use MATLAB, it's very easy. Though there are sometimes you do not uh, come across the accurate solutions using the solver, but that's where the challenge comes. So you have to tune it, you have to change something, and in fact, there are ways to tune or modify the MATLAB inbuilt solver code. So this BVP4C, it is something not something black box. There are several lines. That means the algorithm that is used for BPP4C is already there in MATLAB, kind of this M file. You have to open that and you have to edit it, or you have to change some parameter in that algorithm optimization subroutine or that solver subroutine, so that you can again solve your own specific problem as per your requirement. So this is the reason I introduced the MATLAB, and I emphasize that you learn the MATLAB through this course. It may look like to you that I have covered many things together, but essentially when you go back and study on your own, you will find that the examples problem or the problems that has been discussed in class are supported by the MATLAB code. So it will be not difficult for you to practice it and to understand it. So every day, more or less, some MATLAB examples has been shown to you. So today we have seen another examples considering the boundary value problem. So both IVP and BVP, as well as you see the nonlinear algebraic equations, we have seen, we have spent a good amount of time in understanding the stability of steady states by bringing into the linearization technique concept or some graphical method. So this examples again today is just not just the not just limited to heat transfer across the world, but there can be diffusion across a flat slab, right? Across a flat slab there can be diffusion, and we can again write the similar expressions. Let me just go to that PDF and give you the other different cases that can appear. Okay, thank you, Achal, for your question. Okay, now let me go to this MATLAB file. So now, yes, here. So what I do it written homework 1, homework 2. So basically, you can practice this. It will help you to in the understanding the concepts more clearly. So what we have done here is reaction. First, though I have written reaction, so first let me discuss the easy case, that is the diffusion across a flat slab. So there also we will come across negative sign. I'm not considering, just making it 0. So D, so the second order ODE. And concentration at, let's say, just simple boundary condition at L equals to CL. So we can get a good distribution of the concentration. So D is the diffusivity, which can also depend upon concentration. It can be linearly or non-linearly, and as like previous the K, thermal conductivity, we can also solve the problem in the same manner. So this is the case is basically diffusion across a flat slab. Diffusion across flat slab. Okay, so diffusion across flat slab can be of this. So then we just make the problem little more complicated. Forget the reaction term first. Just consider the diffusion in a spherical pellet catalyst. So let's say you have a catalyst, a particle or catalyst pellet, not particle, catalyst pellet, and inside there are many pores. So gases will enter into the pore and the reaction will happen inside the pore. So maybe I use a different color. So there are some uh, particle called catalyst particle. They are situated inside the pellet. So this catalyst particle are something like you can think of as let me just discuss this. Consider as a so these pores, inside the pore there are surfaces. So this pore is basically can be of cylindrical, can be tortuous, can be a straight pipe type pore, maybe a cylindrical pore, or maybe a some like these pores can be of like this also. So the very different way of pore. So inside the pore your catalyst particles are situated, and those catalyst particles are nothing but ensembles of several atoms, or let's say nickel metals or iron or cobalt. So they are just sitting together making a reasonably large particle size. So cluster of atoms are sitting together. So gases will be adsorbed on the uh, site, on the catalyst site. So inside the pore it is reaction is happening. Okay, so diffusion has to be there. So from the pellet outer surface, diffusion has to be there inside the pore. Now it is told that pellet size is of spherical. So spherical pellet, so accordingly we just use the spherical coordinate. So I'm not going to derive it, but probably you have seen this kind of coordinates or in the terms in spherical coordinate domain. And this equation is coming from the concentration balance, or the basically the mole balance. It is essentially telling you that the rate of diffusion is equals to the rate of reactions, steady state. Steady state diffusion and reaction problem in the, now the reaction has come into picture. Consider that this reaction is not there, so this will be 0, which you can again solve. But consider that reaction is there, which is making your complications, more complications. And then you have introduced, as you can see, that you can also look at the rate at which the reactions as a function of distance. So there is, since there is a spherical pellet, so there are inside the so up to that radius. So let's say this is RP, so pellet radius. So at the pellet outer, what is the concentration and rate of reaction, and at the center what is the concentration and rate of reactions. So accordingly the boundary conditions are given, and for different values of alpha we can plot it and we can solve it. K is something the equilibrium constant or adsorption constant, adsorption equilibrium constant. Since this is a gas phase reaction, so adsorption will be first there. So these values and parameters are provided, and you can solve it, and you will get um, kind of distribution, as I can show you. qualitatively. So it's a very interesting problem. If we get some time, we can try to solve it in Matlab. So concentration will be as a function of this alpha. So if you change the different for different values of alpha, so if this is R 0 and this is 1 and this is concentration, so for different values of alpha though, so something like this it will like this. So for different values of alpha, and alpha increases in this order. So if you solve this for this value set of values and plot the concentration versus R, then this is the behavior. And similarly, you can also calculate, once you know the concentration and R, you can substitute it here and you can actually solve the rate of reaction versus R for different values of alpha, which you can also see as a resultant plot. So R will also vary like this, and for different values of alpha. So just give it a shot. You just try it by writing the Matlab. So all you have to do again, write the function file in boundary conditions and the initial guess. So I would request rather to try it on your own. And I'm sure that there will be some difficulty, there will be some problem, which will also help me to further go into detail and analyze or discuss with it for the subsequent results. So maybe we will interestingly, or we can explore further on this BPV4C technique. This problem is more or less easy, the first problem that we had solved using the Matlab lines. Now there in the second problem, we might have to change the initial guess. We can see the effect of the initial guess. Maybe for this problem, the homework problem, you may try with 0 and 1, but you encounter with problem. Maybe the solution is not converged or solver is unable to solve. So those errors or debugging, it will be easy for us to debug the problem. So just try it in your home for different values of alpha. So you have the code available. So just the heat transfer Matlab code functions, you just change it according to this problem structure. The differential equation is given, boundary conditions given, parameter values are provided. All you have to find out the C versus R and rate of reaction versus R for different values of alpha. First you solve for alpha equals to 0 or alpha equals to 4, and then you just repeat the run, repeat the calculations. You will get different values. So just try it. This part I am not discussing now. This will be later, can be discussed, but at least this problem you try it based on the examples that we have shown in the class, the heat transfer across a slab. Based on that, you can try this reaction diffusion in a spherical catalyst pellet. Okay. So I think that's all for today, and tomorrow from this we will start and try to see uh, we will switch over to the next topic. Few points I had to say from here, then after that we will go to the neural network feed forward algorithm, back propagation method. Okay. Okay, thank you for your attendance. Okay, we conclude the class here.
Thank you, sir.